Good morning, all. Today, in this lecture, I will discuss the method of finding the thermodynamics of ideal gas in quantum mechanical, canonical, as well as grand canonical ensemble. In the previous lecture, we discussed the methods for deriving thermodynamics in quantum mechanical, microcanonical ensemble. So now we will discuss about quantum mechanical, canonical ensemble first. Okay. So the thermodynamics will be derived from partition function in the case of canonical ensemble. The partition function is defined as QNVT. This represents the n particle partition function, and that is given by sum over all energy eigenvalues e raised to minus beta E. Here E denotes the energy eigenvalues of the system of n particles. Now we can define E in terms of the single particle energy states, and it is given by E is equal to sum over epsilon n epsilon into epsilon. Okay, these epsilons are single particle energy states, and here this the number n epsilon should satisfy the condition. If you sum over all the states this n epsilon, you should get total number of particles. Okay, I will explain these two equations. Suppose there are three particles and two single particle energy states. Okay, consider a system having two single particle energy states with energy 0 and epsilon. If there is only one particle, then the energy eigenvalues will be either 0 or epsilon. But the system has now three particles. Then the possible energy eigenvalues of the system will be 0, epsilon, 2 epsilon, and 3 epsilon. So while calculating this n particle partition function, the summation should be over 0, epsilon, 2 epsilon, and 3 epsilon. Okay, that is the total energies possible for this three particles system. I will explain. Here you have two single particle energy states with energy 0 and epsilon and three particles. One possibility is all the three particles in the ground state and no particles in the upper state. Then the total energy of the system will be 3 into 0 plus 0 into epsilon. Okay, three particles in the 0 energy state plus 0 particle in the epsilon energy state. So total energy is 0. That is one of the possibility of the system. Now among the three particles, two particles can sit in the ground state, one particle in the excited state. Then the total energy is 2 into 0 plus 1 into epsilon, that is epsilon. That is one another possibility of energy eigenvalue. Then one particle can sit in the lower state, two particles in the upper state, that will give you 2 epsilon. Then 0 particles in the ground state, 3 particles in the excited state. That will give you 3 epsilon. So these are the various energy eigenvalues of three particle system. I can write the possibilities capital E as summation over single particle states. Here there are two single particle states. So summation goes from 1 to 2. N epsilon into epsilon. That is N1 epsilon 1 plus N2 epsilon 2. If you substitute these values of N1 and epsilon 1, N2 and epsilon 2 for these four cases, we will get 0, epsilon, 2 epsilon and 3 epsilon. So for an n-particle system, the energy eigenvalues can be expressed in terms of single particle energies using this expression. Here, this sum over all single particle states n epsilon should be 3 always. Okay, you can check that. In the first case, n1 is 3, n2 is 0. In the second case, n1 is 2, n2 is 1. In the third case, n1 is 1, n2 is 2. In the fourth case, n1 is 0, n2 is 3. Okay, in all cases, the sum is 3. Okay, that is the meaning of this equation. So, for an n-particle system, the energy eigenvalues can be expressed in terms of single particle energy states. Now, consider a particular distribution set. Okay, a particular distribution set means here you have four distributions. Okay, this is a particular distribution. Two particles in the ground state and one particle in the excited state. This is a particular distribution. Okay, now the partition function Qn of Vt is given by the sum over all distributions g of ne e raised to minus beta sigma epsilon n epsilon into epsilon. I will explain this equation. This is exactly the same equation given by this. Here, this capital E I can replace with the sigma epsilon n epsilon into epsilon. And the sum over all energy eigenvalues means sum over all distributions, because each distribution will give you a particular energy eigenvalue. Then there is one more factor, G of Ne. This is known as statistical weight factor. And the meaning of this is, if your particles are classical particles, for a comparison, I will explain the case of classical system. So if you have a system of classical particles, that is, the particles are distinguishable. So instead of these dots, if I have particles A, B and C, then this distribution can be visualized in different ways. One is AB in the lower state and C in the upper state. The other one is AC in the lower state and B in the upper state. Other one is BC in the lower state and A in the upper state. So there is three possibility. Okay. So for each distribution, if these particles are distinguishable, there are different possibilities. And that is known as statistical weight factor. Okay. Now, if the particles are indistinguishable, quantum system, then these dots, we can use dots to represent the particles, that is, they are indistinguishable. Then for a corresponding distribution, there is only one possibility. Okay, these three possibilities will not be there. This is the case with the classical system. If the system is quantum system, particles are indistinguishable. All these three corresponds to a single distribution. Or we can say that for each distribution, there is only one possibility. That is, statistical weight factor will be 1. So in the case of Bose-Einstein statistics, that is the particles which have symmetric wave function, the statistical weight function is 1. And for Fermi-Dirac case, again statistical weight function is 1, but that is only for number of particles 0 or 1. In the case of fermions, a single particle state can occupy maximum of one particle. Okay, a single particle state can have either 0 particles or 1 particles. Okay, that is the possibility of a fermion system. In the case of boson system, there is no such restriction. A single particle state can occupy or can accommodate any number of particles. But for fermions, a single particle state can accommodate a maximum of 1 particle. So if a state has 0 or 1 particle, then the weight factor is 1. Otherwise, weight factor will be 0. Okay. Now, for the classical case or Maxwell-Boltzmann case, this weight function will be, the actual expression is n factorial divided by n1 factorial into n2 factorial into etc. For example, in this case, you have total number 3 factorial divided by lower level has 2 and upper level has 1. So for this case, the total number of possibilities are 3. So the general expression for finding the total number of possibilities or weight factor is n factorial by n1 factorial into n2 factorial into etc. But if we are considering the case of identical particles, we already discussed about the Gibbs correction in lecture number 4. So accommodating the Gibbs correction factor, this becomes 1 by n1 factorial n2 factorial etc. And I can denote it as pi epsilon 1 by n epsilon factorial. This epsilon runs over all the single particle states. So this is the statistical weight factor for classical system. So that is the only difference. Okay. For a quantum mechanical system, this G of Ne is 1. And for a classical system, this G of Ne is 1 by n factor n epsilon factorial. Okay. Now, this all the single particle states itself we treated as individual states. Okay. In the previous lecture, in the case of quantum mechanical microcanonical ensemble, we assumed that since the energy levels are very close together, we can group some states into a particular cell, and there are a lot of such cells. Okay, our assumption is that a few sets of energy levels combined together to form a cell. But here there is no such concept. Each individual state is treated as single particle state. So GI, the number of energy levels in a particular cell, was GI in the previous lecture. In this lecture, there is no such grouping. So we can take GI as 1. And in the previous lecture, we have the weight factors. The equations are like this. If you put Gi is equal to 1 in these equations, the first one becomes Ni plus 1 minus 1, that is Ni factorial, divided by Ni factorial into Gi is 1. So 1 minus 1 is 0, 0 factorial. So Ni factorial by Ni factorial is 1. For Bose-Einstein, the weight function becomes 1 if you take the Gi is equal to 1. And this equation we discussed in the previous lecture. Now, for Fermi-Dirac case, if you take Gi is equal to 1, this becomes 1 divided by Ni. In the case of Fermi-Dirac statistics, Ni can be either 1 or 0. If Ni is 0, this becomes 1 divided by 0. 1 minus 0 factorial is 1 factorial. So it will be 1. If Ni is 1, this becomes 1 divided by 1 factorial. 1 minus 1 is 0 factorial. Again, you will get the final result 1. But if you put Ni is equal to 2, 3, etc., this is not defined. Okay, negative factorial is not defined. Negative integer factorial. So you will get 0. Okay, weight function is 0. Okay, that is not defined. Then Maxwell-Boltzmann case, Gi raised to Ni by Ni factorial. If you put Gi is equal to 1, you will get pi 1 by Ni factorial. Exactly the same equations. Okay. Now, we will consider the three cases. The first one is Maxwell-Boltzmann case. Second one is Bose-Einstein case. Third one is Fermi-Dirac case. Okay. First one. Qn of Vt is equal to summation over all allowed distributions. Then this statistical weight factor I epsilon 1 by n epsilon factorial. Then you have again a product. Here actually you have exponential of a sum. Exponential of a sum. Okay, and you already know that exponential of a sum is exactly equal to product of exponentials. Okay, exponential of a sum is product of exponentials. I will give you an example. If you consider e raised to minus beta epsilon 1 raised to n1 into e raised to minus beta epsilon 2 raised to n2, then I can write it as e raised to minus beta n1 epsilon 1 into e raised to minus beta n2 epsilon 2. This is nothing but e raised to minus beta n1 epsilon 1 plus n2 epsilon 2, or e raised to minus beta sigma n epsilon e. Okay. So the product of exponentials you can write as exponential of sum. I replaced this exponential of sum with the product of exponentials. That is this step. Now I can insert an n factorial in numerator and denominator. Okay, then the equation will be like this. Okay, now I can apply multinomial theorem. What is multinomial theorem? X1 plus x2 plus x3 plus etc. xm raised to n is equal to summation n factorial by n1 factorial into n2 factorial into etc. nm factorial x1 raised to n1, x2 raised to n2, etc. xm raised to k. Okay, this is true. This is not a km. This is nm. Okay, this is nm. This is true. This equation is true only if n1 plus n2 plus etc. up to nm. These exponents. If you add these exponents, that should give you this total n. Then, and this summation runs over all the values of n1, n2, etc. nm. Okay. If you apply this equation in our case, we have summation over all distributions, and this is exactly n factorial by n1 factorial, n2 factorial, n3 factorial, etc. So you have exactly a term like this. Then you have a product of e raised to minus beta e. So that is exactly like this thing, a product of these terms. So I can apply this multinomial theorem in our case. So sigma prime n factorial n1 factorial n2 factorial etc. e raised to minus beta e1 whole raised to n1 e raised to minus beta e2 whole raised to n2 and so on. Here n1 plus n2 plus etc. up to nm is exactly the total number of particles. So there is no issue for applying multinomial theorem. So that I can write the left hand side as sum of these quantities x1, x2, etc. xm. That is in this case e raised to minus beta e1, e raised to minus beta e2 and so on. That is sigma e raised to minus beta e. Sum over all the single particle energy states. Raised to small n. Instead of small n, we have here capital N. So Qn of Vt is there is a 1 by n factorial and this much quantity we replaced with sigma epsilon e raised to minus beta epsilon raised to n. And in this case, the sigma epsilon e raised to minus beta epsilon is nothing but the single particle partition function. Because here the summation runs over all the single particle energy states. E raised to minus beta e is the Boltzmann factor. So this is nothing but the single particle partition function. So I can write it as Q1 of Vt. So Qn of Vt is Q1 of Vt whole raised to n by n factorial. This result we already obtained in lecture number 3, 4, etc. But this factor 1 by n factorial we have to introduce with the concept of identical particles and using the Gibbs correction. But here this 1 by n factorial comes automatically. Okay, that is the advantage of this treatment. Okay, so this is n particle partition function. Now Q1 of Vt. This we already calculated in many times, but I will do once more. It is sum over all single particle states e raised to minus beta epsilon. Since these single particle states are very close together, if we are assuming a system of very large volume, we can replace this summation with the integration. Okay, then integral 0 to infinity e raised to minus beta epsilon into g of epsilon d epsilon. This g of epsilon d epsilon is degeneracy, that is number of states lying or having energy between epsilon and e plus epsilon. That is known as degeneracy. Now I will calculate the degeneracy in terms of momentum. That is g of t dp is the number of energy levels having momentum between p and p plus dp. Okay, number of states having a momentum between p and p plus dp. This we can calculate using the concept of phase space. This is for a single particle. For a single particle, the phase space is six dimensional. Okay, six dimensional, and the volume of phase space is given by integral d cube d integral d cube q. Okay, and this is the total volume of phase space. But for a particular microstate, there is a certain volume. The volume for a particular microstate is given by h cube in the case of six-dimensional phase space, and in the case of 6n dimensional phase space, it is h raised to 3n. That factor also we discussed in previous lectures. So the number of microstates is given by the total volume of phase space divided by the volume of a particular microstate. Now integral d cube q will give you the total volume divided by h cube. But this integral d cube p, but we have to integrate the region of this shell, that is the momentum lying between p and p plus dp. So what is the volume of this shell? It is nothing but 4 pi p square dp. Okay, so the number of states having momentum between p and p plus dp is v by h cube 4 pi p square dp. Now I can replace this p with the energy using this expression, energy equal to p square by 2m. So p square you can replace it with 2me, and from this equation you can write p as root 2me. So dp is 1 by 2 root 2me into 2m dp. Okay. So substituting all that here, you will get g of e dE equal to v by h cube 4 pi 2m e into square root m by 2e dE. So this is equal to v by h cube 2 pi 2m raised to 3 by 2 epsilon raised to half d epsilon. This epsilon and this epsilon in the denominator, root epsilon in the denominator will cancel. You will get a epsilon raised to half. All these are actually epsilon, not energy. These are single particle energies, epsilon. Okay. Now you can do that integral. Q1 of Vt is equal to integral 0 to infinity v by h cube 2 pi 2m raised to 3 by t raised to minus beta epsilon epsilon raised to half d epsilon. Make a substitution, beta epsilon, call it as t. Then this d epsilon becomes dt by beta, and epsilon becomes t by beta. So substitute for epsilon raised to half, that becomes t raised to half divided by beta raised to half. D epsilon becomes dt by beta. So in the denominator you will have a beta raised to 3 by 2, and this becomes e raised to minus t. All other quantities we take outside. Okay. So this is v by h cube 2 pi. This beta is nothing but 1 by kt. So it is 1 by kt raised to 3 by 2. So that makes it 2m kt raised to 3 by 2. And what is the factor in the integral 0 to infinity e raised to minus t, t raised to half dt? That is nothing but gamma 3 by 2. Where gamma is this just the gamma function. The definition of gamma function is gamma z is 0 to infinity e raised to minus t, e raised to z minus 1 dt. Here you have t raised to half. That is, instead of z minus 1 you have half. So z is 3 by 2. So it is gamma 3 by 2. What is gamma 3 by 2? Gamma 3 by 2 is half gamma half, using the recurrence relation of gamma function, and gamma half is root 2 pi. So this is simply root 2 pi divided by 2. So you will have a root 2 pi here. So that makes it 2 pi m kt raised to 3 by 2. Then there will be this pi, and this root pi makes it pi raised to 3 by 2. That goes to the inside of a bracket. Then there is a 1 by 2 that will cancel with this 2. So the final answer is v by h cube 2 pi m kt raised to 3 by 2. And I will introduce a quantity which is known as mean thermal de Broglie wavelength, and it is given by lambda is equal to h divided by 2 pi m kt raised to half. This is known as mean thermal de Broglie wavelength. Okay, it is a measure of the wavelength associated with the particle which is having an energy kit. Okay. Now, if you substitute that value here, you will get it as V by lambda Q. Therefore, Qn, this is Q1. We have Qn equal to Q1 raised to n divided by n factorial. So that becomes 1 by n factorial into V raised to n lambda raised to 3n. This is n particle partition function in the case of Maxwell-Boltzmann. In the case of systems obeying Maxwell-Boltzmann statistics, that is for classical systems. Now we will consider the case of Bose-Einstein or Fermi-Dirac case, that is quantum systems. Then we know that the weight function is 1. So Qn of Vt is sum or all the distributions e raised to minus beta sigma epsilon n epsilon into epsilon. For Fermi-Dirac case, this n epsilon can take either 0 or 1. For Bose-Einstein case, this n epsilon can take any value. For both these cases, the weight factor is 1. In the case of Maxwell-Boltzmann, the weight factor was 1 divided by n epsilon factor, pi 1 by n epsilon factorial. Okay, instead of this factor, in the case of quantum systems, we have simply 1. Okay, that is the only difference. But the evaluation of this quantity using the restriction sigma epsilon n epsilon equal to n. We have a restriction like this. With this restriction, evaluation of this quantity is very difficult. So we are not going to evaluate at this point. We will move on to the case of grand canonical ensemble. In the case of grand canonical ensemble, the evaluation of grand partition function will be very easy. So this is one problem where you can see the advantage of grand canonical ensemble over canonical ensemble. Okay. Actually, in the case of canonical ensemble, the system can share the energy with surroundings. But in case of grand canonical ensemble, system can share both energy and number of particles. So what is the advantage of grand canonical ensemble? That was a question. And one of the answer is in this problem. Okay. Here the evaluation of canonical partition function is very difficult. But we can see that in the next session, evaluation of grand partition function is very easy. And we can derive the entire thermodynamics using grand partition function. Okay. That is the idea. So we'll discuss now the quantum mechanical grand canonical ensemble. Here the idea is to find the grand partition function theta of zvt. This is the definition of grand partition function. Theta of zvt equal to sum over all the number of particles, sum over n, and sum over energies. Sum over energy, you can replace it with the Qn of Vt, because Qn of Vt already by definition Qn of Vt contains the sum over all energy eigenvalues. What is the meaning of grand canonical ensemble? Grand canonical ensemble, there is exchange of both energy as well as number of particles. That is, for a system in grand canonical ensemble, there is variation for energy and there is variation for number of particles. So the summation should run over all the possible energy values and over all the possible number of particles. So the number of particles in the system is not fixed at n, but it is a variable. It can vary from 0 to infinity. Okay, so there will be two summation. That is the basic difference. Okay, and this is Z is fugacity. Z is known as fugacity. The definition is already done in lecture number 15. Okay, so sigma n equal to 0 to infinity, Z raised to n, Qn of Vt is the grand partition function. Again, we will consider the three different cases. First one is Maxwell-Boltzmann case. We already know that Qn is V raised to n by n factorial lambda raised to 3n. Okay, we just derived this expression for canonical partition function in the case of Maxwell-Boltzmann case. You just substitute this value here. Then this is sigma n equal to 0 to infinity, z raised to n, v raised to n by n factorial, lambda raised to 3n. We know that e raised to x is equal to sigma n equal to 0 to infinity, x raised to n by n factorial. This is the definition of e raised to x. So using that definition, we can write this entire quantity as e raised to zv divided by lambda cube. You can write it as zv divided by lambda cube whole raised to n by n factorial. So grand partition function for classical system is e raised to zv divided by lambda cube. Now we will consider the case of Bose-Einstein statistics. Qn of Vt equal to sum over all the distributions, that is sum over all the energy eigenvalues, e raised to minus beta sigma epsilon n epsilon into epsilon. Evaluation of this quantity is difficult, but grand partition function theta, there is one more summation, sigma n equal to 0 to infinity, z raised to n and sigma prime over all the allowed distributions, e raised to minus beta sigma epsilon n epsilon into epsilon. Now, this z raised to n, I can write this n is actually n1 plus n2 plus etc. So z raised to n is z raised to n1 plus n2 plus n3 plus etc. Where n1, n2, n3 are the number of particles in various single particle energy states. So this can be written as z raised to n1 into z raised to n2 into z raised to n3 and so on. Okay. So this is simply the product. I epsilon z raised to n epsilon. So z raised to n, I can replace it with I epsilon z raised to n epsilon. And this quantity, okay, we already mentioned that exponential of a sum is product of exponentials. So this quantity we will write it like this, product of exponentials. And there are two summations. So these two products combined together, I can write as I epsilon of z e raised to minus beta epsilon whole raised to n epsilon. There are two summations. The first summation runs over all the allowed distribution. Okay? That is, allowed distribution means this n epsilon can take only a few allowed values. For example, in our first example, here we consider one example. If you consider this example, the allowed values of n are, say, for this distribution, it is just 1, n1 is equal to 1 and n2 equal to 2. These are the allowed values. And for this distribution, the allowed values are n1 is equal to 3 and n2 is equal to 0. So for each distribution, there is particular values for this n epsilon. Okay, n epsilon. So the first summation goes over all that allowed values of n epsilon. But if you consider the second summation, here it can run over all the possible values of n. In the first case, the summation is over all the allowed values of n epsilon, where we have one condition that total n is fixed. Okay, in our earlier case, that n was 3. Okay? In this example, we fixed the total number of particles as 3. Then we calculated the various, or we uh, observed the various distributions. Okay. Now, if you vary that capital N from 3 to 4, 4 to 5, etc., then this n epsilon will also take all the allowed values. N epsilon will also take all the allowed values. That means this double summation we can replace with a single summation over all the possible values of n1, n2, etc. For a fixed n, this n epsilon can take only limited values. But if you vary the capital N from 0 to infinity, then it is definite that this n epsilon will take all the possible values, So we can replace that double summation with the single summation over all the possible values of n1, n2, etc. So I can write this independently. Sigma n1 z e raised to minus beta epsilon 1 raised to n1. Sigma n2 z e raised to minus beta epsilon 2 raised to n2, and so on. This n epsilon can take any integer value from 0 to infinity. 0 to infinity. Now, we already have a relation like this. Sigma t raised to n is 1 by 1 minus t. And this is applicable only when t is less than 1. Sigma t raised to n is 1 by 1 minus t, provided t is less than 1. So here we have sigma, instead of t, z e raised to minus beta e1, epsilon 1. Okay. So I can write the first term as 1 by 1 minus z e raised to minus beta epsilon 1. Second term will be 1 by 1 minus z e raised to minus beta epsilon 2, and so on. So this is simply the product pi epsilon 1 by 1 minus z e raised to minus beta epsilon. This pi runs over all the single particle energy states. And the condition is for all single particle energies, z e raised to minus beta e should be less than 1. For all epsilon values, z e raised to minus beta epsilon should be less than 1. Then only this equation is correct. And this is the grand partition function in the case of Bose-Einstein. In the case of Fermi-Dirac case, this n1, n2 cannot take any value. It can take only 0 or 1. Okay, each single particle state can occupy by a maximum of one particle. Okay, the single particle state can be empty, or it can contain a maximum of one particle. So n1 can take either 0. If n1 is 0, you will get it as some quantity raised to 0, it is 1. If n1 is equal to 1, you will get z e raised to minus beta e1. So first term will be 1 plus z e raised to minus beta epsilon 1. Second term will be 1 plus z e raised to minus beta epsilon 2, and so on. The product of all this, I can write it as pi epsilon 1 plus z e raised to minus beta epsilon. Again, this pi runs over all the possible single particle states. Okay, so this is grand partition function for Fermi-Dirac case. Now we know that a Q potential or grand potential, there is a quantity like grand potential, and from this quantity we are going to derive all the thermodynamics of the system, and the definition of this is already done in lecture number 50. Q potential is given by Q of ZVT, it is equal to PV by KT, and it is logarithm of grand partition function, log theta. If you substitute this value of theta, in the case of Bose-Einstein case, it is log pi epsilon 1 by 1 minus z e raised to minus beta epsilon. Logarithm of a product, ln of a, b, c. You can write it as sum of logarithm, log a plus log b plus log c. Okay, logarithm of a product is sum of logarithm. So this product will get replaced with sigma. Logarithm of 1 divided by, I can write it as minus of logarithm 1 minus z e raised to minus beta epsilon. Because logarithm of 1 by a is nothing but minus log a. Okay, so I used this relation and I used log abc as the sum of logarithms. Combined these two, I can write for Bose-Einstein case the Q potential as minus sigma epsilon log 1 minus z e raised to minus beta epsilon. In the case of Fermi-Dirac, it will be logarithm of this quantity. So this product will become summation sigma epsilon log 1 plus z e raised to minus beta epsilon. So this upper sign, this negative side denotes Bose-Einstein case. This positive sign denotes Fermi-Dirac case. I can express both as a single expression. Okay, both as a single expression. In general, I can include all the three cases in a single expression. Q potential is given by 1 by A sigma epsilon log 1 plus Az e raised to minus beta epsilon. In the Maxwell-Boltzmann case, you have to take this A tends to 0. If you take A tends to 0, log 1 plus x. What is the expansion of log 1 plus x? It is x minus x square by 2 plus x cube by 3 and so on. But if x is very small, you can neglect the second order terms or higher order terms. So just keep this first term itself. Then 1 plus log 1 plus az e raised to minus beta epsilon becomes simply az e raised to minus beta epsilon, and that a will cancel with this a. So you will get z into sigma epsilon e raised to minus beta epsilon. Sigma epsilon e raised to minus beta epsilon is nothing but single particle partition function. So it is zq1. Okay. For Maxwell-Boltzmann case, grand potential is given by zq1. This result we already derived in lecture number 16. If you put a equal to minus 1, you will get Bose-Einstein case. If you put a equal to plus 1, you will get Fermi-Dirac case. So using a single expression, you can represent all the three cases. If you substitute a tends to 0, you will get Maxwell-Boltzmann. If you put a equal to minus 1, you will get Bose-Einstein. If you put a equal to plus 1, you will get Fermi-Dirac case. Okay. Now, from the results of grand canonical ensemble, we have two equations, important expressions. One is for average number of particles in bar. Second one is for average energy E bar. We are considering a system in which the number of particles and energy is variables. Okay, number of particles is a variable, energy is a variable. In the case of the system in grand canonical ensemble, so it is natural to find the average number of particles and average energy. What is average number of particles? From lecture number 15, you can see that the general expression is Z dou Q by dou Z at a constant volume and temperature. Okay, so you have a Z, then dou by dou Z of Q. The expression for Q is 1 by A into this quantity. So 1 by A will come outside. Sigma epsilon. What is the derivative of logarithm? It is simply 1 divided by 1 plus Az e raised to minus beta epsilon. But derivative is with respect to z. You have to take the derivative of this term once again. The derivative of 1 is 0. Derivative of Az e raised to minus beta epsilon with respect to z. It is A e raised to minus beta epsilon. This A and this way will cancel. This z into e raised to minus beta epsilon will go to the denominator. Then this 1 by z e raised to minus beta epsilon becomes z raised to minus 1 e raised to beta epsilon plus this quantity z e raised to minus beta epsilon will cancel. You will get A. So n bar is sum over all single particle energy states 1 divided by z raised to minus 1 e raised to beta epsilon plus A. What is E bar? E bar is by definition it is minus dou q by dou beta at the constant zb. So take the derivative with respect to beta. You have minus 1 by a. This 1 by a is from here. Again summation. What is the derivative? Logarithm derivative is 1 divided by 1 plus az e raised to minus beta epsilon. Derivative is with respect to beta. So that will give you minus epsilon az e raised to minus beta epsilon. Again a will cancel. This minus and this minus becomes plus. There is an epsilon in the numerator. A already cancelled. Z e raised to minus beta epsilon will go to denominator. That will make it z raised to minus 1 e raised to beta epsilon plus a. So the only difference of n bar and e bar is a factor of epsilon. Okay, this is average number of particles and this is average energy of a system in grand canonical ensemble. Now I will discuss the most important aspect, the statistics of occupation numbers. Statistics of occupation numbers. We have theta zbt, the grand partition function. Some or all n values and some or all the distribution or all the energy eigenvalues e raised to minus beta sigma n epsilon into epsilon. If you take the partial derivative of this theta with respect to one of the energy eigenvalue epsilon, okay, this epsilon can take different values. These epsilon are various single particle states, energy of various single particle states. You consider any one of the state, okay, keeping all other energies constant, you vary the energy of a particular single particle state. Okay, dou theta by dou epsilon, take the derivative of theta with respect to epsilon, keeping all other epsilons and zt constant. Then you will get this term constant, n equal to 0 to infinity z raised to n, and sigma prime e raised to minus beta sigma epsilon n epsilon into epsilon multiplied with function of a function rule. The derivative is with respect to epsilon, then that will give you minus beta n epsilon, minus beta n epsilon. If you take this minus beta to the left hand side, this is minus 1 by beta dou theta by dou epsilon equal to this summation and this summation into this ne. If you divide it with the grand partition function, then it becomes 1 by theta into this quantity, and that is equal to right hand side you will have this numerator divided by theta, divided by theta. What is this quantity? This summation, except this summation, if you consider this quantity z raised to n e raised to minus beta into sigma epsilon n epsilon epsilon divided by theta, that is nothing but the probability, equation for probability in grand canonical ensemble, and multiplied with this n epsilon, that will give you the expectation value or mean value of that quantity, and that is defined as the uh, occupation number of a particular level. Okay, we have this definition for expectation value or mean value, sigma n epsilon into p epsilon, where p epsilon is the probability. And in grand canonical ensemble we have the equation for probability as z raised to n e raised to minus beta e capital E divided by sum over all states this quantity, and that is that summation is nothing but the grand partition function theta. Okay, so you can replace this right hand side with this expectation value of n epsilon, and that is nothing but the occupation number. Now consider this quantity minus 1 by beta dou q by dou epsilon. Okay, q is nothing but log theta. So this is minus 1 by beta dou by dou epsilon of log theta, and this is dou by dou epsilon of log theta is nothing but 1 by theta into dou theta by dou epsilon, 1 by theta into dou theta by dou epsilon, and this quantity is exactly you have in this left hand side. Okay, so this left hand side you can replace it with the this quantity minus 1 by beta dou q by dou epsilon. So occupation number is given by minus 1 by beta dou q by dou epsilon, keeping z, t and all other epsilon values constant. This is the equation for occupation number. We already have an expression for q, 1 by a sigma epsilon log 1 plus az e raised to minus beta epsilon. Substitute here in this expression, we have to take the derivative with respect to a particular epsilon. This is actually a sum, and it sums over all the possible values of epsilon. You are taking partial derivative with respect to a particular epsilon. Then that single term will contribute to this derivative. All other terms will vanish. So there is no more summation from now onwards. So this is 1 by A. Among this sum, only the term with that particular energy eigenvalue will contribute, and that is logarithm of the derivative of logarithm term is 1 by 1 plus az e raised to minus beta epsilon. Derivative is with respect to epsilon. So you have to take function of a function, then that will give you az e raised to minus beta epsilon into minus beta. This minus beta you can take it to the left hand side. So a and a will cancel. Z e raised to minus beta e will go to the denominator, and that becomes 1 by z raised to minus 1 e raised to beta epsilon plus a. This is the final expression for occupation number. Okay, the average occupation number is given by, this is occupation number in the single particle energy state with energy epsilon. Okay, that is the average number of particles in a particular single particle energy state with energy epsilon is given by 1 divided by z raised to minus 1 e raised to beta epsilon plus a. This set is fugacity, and we know that fugacity is e raised to minus alpha, and alpha is minus mu by kt. So Z is e raised to mu by kt. Mu is known as chemical potential of the system. So if you substitute for this set, you will get 1 divided by e raised to epsilon minus mu by kt plus a. So this is if you have various single particle states like this with different energies. Okay, this have energy say E1, E2, E3 and so on. So this NE1, occupation number NE1 is nothing but the average number of particles in the single particle state with energy E1. NE2 is average number of particles in the single particle state with energy E2 and so on. That is the meaning of this number. Okay, for a particular system, what is the average number of particles in each single particle state? That is mean by the occupation number. Occupation number. I will explain this quantity more. Consider the plot of this occupation number versus this variable epsilon minus mu by kt. You consider this plot. You call this epsilon minus mu by kt as x, then that expression for occupation number becomes n epsilon is equal to 1 divided by e raised to x plus a plus a. Now we will consider the three different cases. If you put a equal to minus 1, you will get Bose-Einstein. If you put a equal to 0, you will get Maxwell-Boltzmann. If you put a equal to plus 1, you will get Fermi-Dirac case. And the graph of these three cases is shown here. Bose-Einstein case is shown in yellow. Maxwell-Boltzmann is shown in green. Fermi-Dirac is shown in red. Okay. What is the meaning of these three graphs? I will explain one by one. First one is Fermi-Dirac case. Here A is plus 1. A is plus 1. Okay. A is plus 1. So that equation for occupation number becomes 1 divided by e raised to epsilon minus mu by kt plus 1. We know that exponential e raised to x is always greater than 0. E raised to x can never be negative. For any value of x, e raised to x is greater than 0. So 1 divided by 1 plus a quantity which is greater than 0, that will result always in a quantity that is less than 1. Okay, if you have a quantity 1 by 1, that is 1. If the denominator increases, then the value will decrease. So e raised to e minus mu by kt is always greater than 0. So occupation number is always less than 1. For any single particle state, in the case of Fermi-Dirac, the occupation number is less than 1. That is a result we already expected, because in the case of Fermi-Dirac case, a single particle state can occupy either 0 particle or a single particle. So the occupation number will be less than 1. Okay. Now, for epsilon less than mu, if epsilon is less than mu, this quantity will be negative. For epsilon less than mu, this exponential raised to a negative quantity. And suppose this e minus mu by kt, the magnitude is very high. Suppose the magnitude of this quantity is very high and its sign is negative. So this becomes e raised to minus infinity. E raised to minus infinity is 0. So you will get it as 1. 1 by 1, 1. So for epsilon less than mu, in the limit, this quantity is very high. This occupation number will tend to 1. That is the meaning of this region. For epsilon less than mu means x less than 0. Okay, epsilon less than mu means x is negative. So less than 0. Here, as you go to the region of minus infinity, that is modulus of e minus mu by kt tends to infinity. This Fermi-Dirac case, that tends to 1. This actually, this is 1. This is 1. So for Fermi-Dirac case, the maximum occupation number is 1, and that happens in this limit. Okay, that is the explanation of this graph. What about x equal to 0? That is when e or epsilon is equal to mu, then this e raised to 0 becomes 1. So it is 1 by 1 plus 1. It is 1 by 2. 1 by 2. That is why for this red line, at x equal to 0, it crosses through half. Okay. So that is the explanation of Fermi-Dirac case. Now, Bose-Einstein case. A is equal to minus 1. A is equal to minus 1. Also, there is one more restriction. This z e raised to minus beta epsilon should be less than 1. That restriction we already discussed here while writing the grand partition function of Bose system. We have this expression, and in order to write like this, there is a condition: z e raised to minus beta epsilon should be less than 1. Okay, so keep in mind this. For Bose-Einstein system, this quantity z e raised to minus beta epsilon, for all epsilon values, it should be less than 1. Now, what is that? E raised to mu by kt. So, this quantity is e raised to mu minus epsilon by kt. This is always less than 1. This is always less than 1 means e raised to 0 is 1. E raised to a positive quantity is always greater than 1. So, less than 1 means e raised to this quantity should be negative. That is, mu should be less than epsilon. And epsilon is various single particle energies. So the chemical potential of the system should be less than all the single particle energies possible for the system. The chemical potential of a system, in the case of Bose-Einstein, chemical potential should be less than all the possible single particle energies of the system. Now suppose the lowest possible energy is ground state energy E naught. Then if mu approaches that value, okay, mu should be less than or epsilon, and the lowest value is ground state energy epsilon naught. When mu tends to this value, this quantity mu minus epsilon will tend to 0, e raised to 0 tends to 1, and for Bose-Einstein case, this is e raised to x minus 1. So when this approaches 1, this will denominator approaches 0 and occupation number tends to infinity. This is the basic reason for Bose-Einstein condensation. So, what is Bose-Einstein condensation? The ground state, if you vary temperature at a particular temperature, the ground state, the population of ground state becomes infinity. That is, more and more particle will accumulate on the ground state. If you have different single particle energy states, E1, E2, E3, E4, etc., this mu should be less than all these energy values. So that means mu should be less than the lowest one, epsilon 1. So when this mu approaches the value epsilon 1, this occupation number tends to infinity. Okay, so if you vary temperature, you can make all the particles accumulated on this ground state, and that is known as Bose-Einstein condensation. Bose-Einstein condensation that we will discuss in the coming lectures. Now, for mu less than epsilon, this E minus mu is positive. E minus mu is positive. So occupation number is 1 by e raised to e minus mu by kt minus 1. Okay, e raised to e minus mu by kt is positive, means this quantity will be greater than 1. This quantity will be greater than 1, and we will get a non-singular value for occupation number. Now consider the Maxwell-Boltzmann case, that is a equal to 0. A equal to 0. Then occupation number becomes 1 by e raised to epsilon minus mu by kt plus 0. This I can write it as e raised to mu minus epsilon by kt. So I can write the occupation number proportional to e raised to minus epsilon by kt. That is, as you move to the higher states, these are various single particle energy states. If you go up, then the occupation number decreases. That is the case with the Maxwell-Boltzmann case. As energy increases, the occupation decreases. Okay, so the most of the particles will occupy the ground states. As temperature increases, there is possibility of occupation of higher levels. If you fix this temperature and all, as energy increases, the occupation decreases. That is the case with the classical system. Now, for all cases of practical interest, this quantity e raised to e minus mu by kt is very much greater than 1. That is, this occupation number will be very much less than 1. What is the meaning of occupation number very much less than 1? Suppose you have a lot of levels, and assume that some levels have particle 1 and most of the levels are empty. Okay, only few levels have one particle and all other levels are empty. Then the average occupation number of all these levels will be very much less than 1. Okay, average of this occupation number will be very much less than 1. And if some states have more particles, that is, if the density of the system is very high, then the value of occupation number will be greater than 1. So occupation number very much less than 1 means there are a lot of single particle states and the number of particles are very low. So probability of any of the n epsilon being greater than unity is quite negligible. That is the meaning of this statement. Occupation number very much less than 1 means probability of any of the n epsilon being greater than unity is quite negligible. And in that case, this weight factor we have for classical case or Maxwell-Boltzmann case, the weight factor is 1 by n1 factorial, n2 factorial, etc. If this n1, n2, n3 can take only 0 or 1, can take the values either 0 or 1, this becomes 1 by 0 factorial, 1 factorial, 0 factorial, 1 factorial, etc. So the final result will be 1. If any of this number will take a value greater than unity, this will not be 1. So if the occupation number is very much less than 1, that means all the n epsilon values will be either 0 or 1, then this g of ne will be 1. That is, there is no distinction between classical case and quantum mechanical case. The only difference between classical and quantum mechanical case is in this weight function. If you are considering a system with occupation number very much less than 1, then this g of ne will also be 1. So the distinction between classical treatment and quantum mechanical treatment becomes insignificant. All the three curves merge together. When this occupation number very much less than 1, all the three curves merge together. You can see this graph. When occupation number very much less than 1 means this region, this portion. This y-axis is occupation number, and that is very close to 0 means here. So all the graphs merge together for very low values of occupation number. Okay. Now, we also know that larger the temperature, larger the validity of classical treatment. For a particular system, if you want to use the classical treatment, the conditions are temperature should be very high and density, number density should be very low. That is the conditions for the validity of classical treatment. And we also know that from this expression, for very low value of occupation number, this quantity e raised to epsilon minus mu by kt should be greater than 1. Okay. For this to be greater than 1, this mu should be very large negative value. If this chemical potential is very large and it is negative, this this factor will be very large and e raised to that quantity will be very much greater than 1. So in order to make this quantity very large, this mu should be large negative. If mu is large negative, that means z is very much less than 1. Z is very much less than 1. But from grand canonical ensemble results, we have capital N is equal to ZV f of t, and f of t is nothing but 2 pi m k t raised to 3 by 2 by h cube. So this can be written as ZV divided by lambda cube, or Z is equal to n lambda cube divided by V. What is this n by V? Total number of particles by total volume. It is number density, small n. So set less than 1 means n lambda cube less than 1. Set less than 1 is the condition for the validity of classical treatment. Then we can write in terms of number density and lambda the condition as n lambda cube less than 1. This is a very important criterion. If the number density multiplied with lambda cube, lambda consists of temperature in the denominator. So if the number density is very low or temperature is very high, both will make this quantity very much less than 1. Number density low or temperature very high, both will make this quantity very much less than 1. And that is the condition for validity of classical treatment. Okay. For getting the correct results using classical assumptions, the number density of system should be very low and temperature should be very high. Otherwise, we have to use the quantum mechanical results. So this is a criterion for the validity of classical treatment. N lambda cube should be very much less than 1. Okay, thank you.